We will now talk about ASA fundamentals and basic configuration. Cisco ASA is an example of an advanced next-generation firewall, which means that this device is going to offer some sort of sophisticated functionality compared to regular stateful firewalls. Well, obviously, it still provides those stateful filtering capabilities like any other regular stateful firewall does. But those capabilities, in case of the ASA, are pretty extensive. It allows us to not only inspect communication at layer 3-4, it also allows us to go up to the application layer. It allows us to configure and tune some of the application layer settings or just the behavior of the inspection engines. And in case of certain protocols, the inspection options will be pretty sophisticated. The device is also going to act, or just can act, as a VPN termination point. So we can configure our firewall as a site-to-site gateway or as a remote access gateway to our internal networks. And it supports pretty much every single commonly used secure VPN mechanism like IKE version 1 and 2 for IPsec and also SSL. This device is also acting as a next-generation intrusion prevention system when we couple it with the firepower inspection module. It also offers advanced functionality like, for example, reputation-based URL filtering and advanced malware protection. It is also possible to virtualize a single physical unit into multiple logical firewalls, like when you want to use many different firewalls at different places of your network without having to buy separate physical devices. So we could use this feature to, let's say, sell firewall services to your customers, or, for example, to configure different firewalls, deploy different firewalls for different departments. The ASA is also supporting highly available networks. We can deploy ASA firewalls in a redundant fashion, and this can be accomplished by using either failover or clustering solutions. There are two major ways how we can deploy our ASA. We can either go for a physical appliance. Specifically, this is going to be the 5500X series of ASA firewalls. And here, the higher the number is, generally the more performance it offers. So we're going to be talking about things like the overall bandwidth available on the interfaces, like the bandwidth for the firewall. And we will be talking about the inspection capabilities, like how many connections per second can be inspected. The platform is also going to affect things like a VPN peer number and some other settings. And then the second way to deploy the ASA is going to be to use a virtual image, which is going to be installed on a VMware server. There are going to be 3 images to choose from, 5, 10, and 30. And the only difference between those images is going to be the throughput supported by one or another image. The main drawback of a virtual ASA is that it does not support virtualization, or just multiple contexts, and clustering, but it is still commonly deployed in the data centers. One of the first things that we will have to do when we deploy a new ASA into the network is going to be to configure its interfaces. And first and foremost, we will have to select the actual type of interface we want to use, or just interface mode. There are going to be a few different options here that we can choose from. First and foremost, the simplest solution is going to be to configure a physical interface of the ASA. Just take a single physical port, like Giga1, and configure it. Then the other option is going to be to combine 2 physical interfaces, make them redundant, and then one of those ports is going to be acting as a standby. The other one is going to be the active port. So just one of these 2 interfaces is going to be physically forwarding the traffic, and the other one is waiting for the active interface to go down. So this is how you can build redundancy at that interface level. It is also possible to combine 2 or more interfaces and make them all active, like when you bundle those interfaces into a single logical port, known as a port channel. So the feature is called Ether channel, but the logical interface is called port channel, and this logical port channel interface is going to represent the underlying physical ports to the layer 3 or layer 2 processes. So in this case, multiple interfaces will be active in the same time, and it will be possible to distribute the packets across multiple bundled interfaces. So we will not only provide redundancy, but also increase available bandwidth. And it is also possible to build logical interfaces, which is implemented in the exact same way as on iOS devices. So we can build a subinterface of a physical port, and the device will separate the packets between those logical interfaces by using layer 2 trunking. And it must be 802.1q what you'll configure on the switch if you want to use that feature. So the ASA is going to connect the switch as a trunk, and you will have to select 802.1q on the switch because this is the only trunking protocol supported by the ASA. Once the trunk is up, you will be able to configure logical interfaces on the ASA by using that interface command when you specify the name of the physical port followed by a dot and a number. Okay, once we selected the interfaces for our deployment, we will then have to logically configure them with certain settings. So first and foremost, we will have to configure our interface with an IP address. It could be version 4 or version 6 address. It could be both. Remember that when you configure a version 6 address on the ASA, it automatically enables version 6 routing. So it's not like on iOS where you have to say IPv6 unicast routing. This command is not needed on the ASA, so it starts forwarding version 6 packets. Okay, then probably the most important setting for the interfaces is going to be to configure a so-called security level, which is just a number between 0 and 100 that describes how trusted or untrusted a given interface is. And this number is going to have a serious implication on how the ASA is going to, by default, filter the traffic. Because as we will see, the traffic that is generally coming from a more trusted interface is going to be allowed, versus traffic which is coming from a less trusted network will be blocked. Okay, then we will have to configure an alias for our interface, which is needed to kind of like activate the interface for traffic forwarding. So we'll have to give it a logical name, which is like a description of a security zone that we configured with our security level. It could be something like inside, outside, DMZ. Whenever you call it inside, the device is also going to assume a security level of 100. Whenever you use a different name, it is going to assume a security level of 0. Okay, next optional element is going to be to configure a VLAN number or just a VLAN tag if you want to use or just build a sub-interface. So this is optional. And remember that ASA does not support DTP, or just dynamic trunking protocol, so you will have to configure a static trunk on the switch to the ASA with 802.1q encapsulation enabled. And also, if you plan to use main or just the physical interface for a traffic forwarding, you will have to configure just a native VLAN on the trunk. And the last step is going to be to physically bring the interface up with the no-shut command. Okay, so as I said, the ASA is going to, by default, once we enable the interfaces, and this way initialize the firewall, is going to come up with some sort of a logical default filtering policy, which is going to generally rely on the security levels configured on our ports. And as a general rule, the ASA is going to, by default, allow communication originated on a more trusted interface, which is going to be an interface configured with a higher security level when a packet is destined to a lower security level interface. And for the opposite direction, so when a packet originates on a lower security level interface, it is destined to a higher security level interface, the ASA will drop the packet. And it is possible to make exceptions to the second rule by configuring and applying an access list. Okay, so let's say that we have a firewall. Like in a common design, we're going to be using 3 different interfaces, one connected to a single zone. Like let's say that this is going to be our inside, this is going to be the outside, And we will also have one more, which is going to be our DMZ. So in many common deployments, what you will do here, when you will then configure those interfaces, is that you will then assign them the following security level numbers. You will go for something high for your inside, like for example, 100, which is the highest number. You will go for something semi-trusted, like 50 for the DMZ, and then outside is going to be typically configured with a level of 0. So this configuration, once the interfaces are up, it also automatically enforces a policy on the packets traversing through the firewall, which is going to be to allow communication from a higher to lower security level interface and block communication going in the opposite direction. So this means that when the packet is originated on the inside, it is able to go out through any other interface, because in our case, all other interfaces are configured with a lower number. So since 100 is the highest number here, it is greater than 50, and it is also greater than 0, the packet is allowed in any direction, from the inside to the outside, from the inside to the DMZ. Now, from the DMZ's perspective, it means that the packet is going to be allowed to the outside, but not to the inside. This one is going to be blocked. And the reason for it is that 50 is less than 100. So obviously this also means that packets originating on the outside, no matter if they are destined to the inside or DMZ, they will be blocked because 0 is the lowest number here. Okay, it is also possible to configure two interfaces with the same number, with the same security level, and by default the communication between those interfaces is gonna be blocked. If you want to change this behavior, you'll have to use the same security traffic permit inter-interface command. And then a somewhat similar situation is when you want to route a packet back via the same port where the packet was received on. So for example, when a packet is coming on the outside and the device is trying to route it back via outside, this is going to be by default disabled. If you want to enable it, you will have to use same security traffic permit intra-interface option. And when you enable it, this is going to be known as hairpinning or U-turn. This feature is going to be useful in certain VPN scenarios. Like for example, when we have a remote access tunnel. So when someone is connecting to our network using, let's say, SSL or maybe IPsec VPN, we have the ASA firewall, which is connected to the internal network. Then we have the public network. And finally, a client which is connecting, which is building that VPN tunnel. So the tunnel is built from the PC to the outside of the ASA. This is our VPN. So this feature is going to be useful when split tunneling for that VPN is disabled, which means that all packets generated by the PC are destined to the tunnel endpoint, to the ASA. All communication. No matter if the PC is trying to reach some internal destinations, but also if PC is trying to get to public devices, like for example to a web server connected to the internet. So even though the packet is destined to that internet device, it is still tunneled with split tunneling being off, which would mean that unless you have some other exit point here to the internet in this internal network, the ASA would have to route the packet back for the same interface where it received it on. So the ASA got the packet on the outside, and so the client can connect to the public server. The ASA must send the packet back via outside, and then when it gets the reply, it is going to tunnel the reply back to the client through the VPN tunnel. So this would be an example where you would have to enable U-turn or just hairpinning on the outside port so that the ASA can route packets back. Okay, one more thing we will also discuss in this session. It's going to be just a quick overview of how the ASA is routing packets. So the process is going to be very similar to what an iOS device does, which means that our firewall is going to be generally using a routing table to select the egress interface for a packet. So it's still based on the longest match, what the device is trying to find in the routing table. And this match is then selected to find the egress interface for a packet. Like if the interface is directly connected, or if the route points to a next hop, the ASA is going to do the route recursion to find the egress interface. Finally, when we have that interface, we will switch the packet to the egress port, we will re-encapsulate it, and serialize the packet onto the link. But there is going to be one difference from iOS devices, specifically when a packet is going to match an existing translation. Like for example, we translated an internal device 10.1.1.1 to a public address 1234, and a packet is destined to 1234. This would mean that our packet would match a translation entry, and this entry would be used to find egress interface for that packet and not the routing table. So this is the default behavior of the ASA unless your translation was configured with the route lookup option. But other than that, the routing process is going to be the same as on iOS. So the device is going to be using routing table to find the longest match. Then it is going to use the next hop or just the egress interface to switch the packet, and finally re-encapsulate the packet and serialize the packet onto the link. And just a summary of the routing configuration for most commonly deployed routing protocols. Just a really basic config to show you the very basic syntax. So in case of static routes, we're going to be using that route or IPv6 route command to configure a static path. If you want to build a default route, you will be using 00 to specify a 0.0.0 prefix with the same subnet. And the main difference from iOS is that you will have to select or just specify an interface which is going to be associated with a given route. Okay, in case of OSPF for IP version 4, we're going to say router OSPF, then specify the process number, and use the network command to enable OSPF on certain interfaces, and also to advertise networks configured on those interfaces. Same exact configuration as on iOS. And then for OSPF version 3, like on iOS, we will first thing have to build a process globally. So IPv6 router OSPF a process number, and then enable this process on individual interfaces with the IPv6 OSPF command. And then for EHRP, like on iOS, define the AS and enable your interfaces and advertise the subnets configured on those interfaces with the network command.